Okay, let's go to the first example here of using L'Hopital's rule. All right, so what I want to do is set up the example here of a specific rational function. You're taking the limit as x goes to 0, the sine of x minus x over x squared. And first, if the idea is if we're trying to take the limit of this function, we plug in the zeros and see if it works, see what we end up with. And you plug in 0 to the numerator and you end up getting the example that's shown here, that if you plug in 0 to this function, you end up getting sine of x minus x. You get 0, sine of x is 0, and x, just plug in 0 here, you get 0. So we have 0 on top. The derivative, and plug in 0 to x squared into x squared, you end up with 0. So we have an indeterminate form at 0 of the type 0 over 0, which qualifies for using L'Hopital's rule. That's the idea of determining if it's an indeterminate form. So what we're able to do is use L'Hopital's rule, which says taking the derivative of the top and the derivative of the bottom will end up giving us the same limit. It will qualify as being the same limit as the original problem if you take the derivative of the top and the derivative of the bottom. So we take the derivative of the top, and we get the derivative of sine is cos, and the derivative of minus x is minus 1, and the derivative, and that's the numerator, and the derivative of the x squared is 2x on the bottom. So again, we take the limit as x goes to 0 of the derivative of the top and of the derivative of the bottom and see what we get. Notice they went through and took the 1/2 out. They took the denominator, the constant that was the coefficient, and took it out front. And you don't have to do that. You would get the same result if you left that as 2x. This is a way of being efficient, so to speak, cleaning it up a little bit. But it would have been fine to leave it in there. But now you plug 0 into this function for x and 0 into x for this function, and see what you get. You take the cosine minus 1. The cosine of 0 is equal to 1, and 1 minus 1 does give us 0 again. And the limit as x goes to 0 of x is also 0. So again, we verify that it is of the indeterminate form 0 over 0. So you do it again and verify what happens. So you start from where you left off, which was here, cosine minus 1 over x, and you take the derivative of this term over the derivative of this term, here and here. The derivative of cos is minus sine. The derivative of minus 1 is 0. And check out the bottom, the derivative of x is 1. And as a result, you end up with 1/2, or it could have been a 2 down there, because the derivative, if we had left 2x down there, the derivative of that would be 2 instead of just 1. But then as x goes to 0, you end up with 0 over 1, which is 0. So remember, there are some students in the past, when they see 0 over 0, they think that that answer is 0. And that's not the answer of 0. This is of the type, you get 0 in the numerator and 0 of the denominator. That's the indeterminate form of the type 0 over 0. So you took the derivative, and at the top, derivative at the bottom, and had to do it twice. And then after the second time, we end up with, when you plug in the limit as x goes to 0, you get the value of 0 for your answer. So that is the answer for what the limit as x goes to 0 of the original function is. You can confirm that by looking at a graph of the situation on your calculator and see that 0 does match this. But that is the first example of using L'Hopital's rule. Okay, we've got another one coming up shortly.